is on the back. So from you have septic tank, then there will be phosphoridec filter, and then it goes to the drainage and to the stream. And here are just a few examples of international projects. So in 2009, we were invited to go to Taiwan, where I presented our results, and people actually had vision. So somebody invested in our system demonstration project at the university, at National University of Science and Technology in Pingtung. And they already had this structure as 3 lines. So it was very convenient. We excavated what was inside, and we built 3 different lines as for comparison of different type of configurations in the systems. And the system had only, it was collecting water from residential halls of residence, from the students, and it only had primary treatment. It only had grit removal and sand filter that was not working properly. So it was like a polishing step testing for phosphoridec. And it was performed for 220 days. We had a graduate student who was working on this project. And we obtained really excellent removal efficiency, as I said, which later impressed our governmental officials in US. But we ran different, I will not go into details, but you can see on the slides in the printout, we had 4 different runs. And again, in Taiwan, I have to explain, in Taiwan, unlike in the United States, it's the universities that perform technology validation. So there is no special institution. So in this case, even though there are like over 300 universities in Taiwan, which is very small, there are 2 universities that perform this kind of validation. So it was the professor with whom I worked that selected the conditions which I had to run and work on in order to prove whether the system works or not. The major point in this system was, so if you are watching from this side, the water was flowing in this side, there was this little nice space where I could test in Taiwan our pH reducer. Because something that I didn't say before is that something that sets phosphoridec systems apart from other technologies is the fact that we have developed special kind of filter to diminish pH. And so we can build this as a part of our unit, or we can do it as an add-on unit on the system. And so we tried to test this in Taiwan, but what happened was this unit had really poor, extremely poor hydrological design, because when your effluent from slag was coming here, and then there was really no mixing. This is just 30 centimeters wide, and the water was coming to the outflow. It was very hard to get any kind of contact between the material in a pH reducer unit. And so we just built this little pipe trying to distribute water better. And to my surprise, they were not selling pipes with the holes, we had to drill them. But so we invented something to try to improve this infiltration a little bit. And then I put some plants because I really loved this water research center, and I thought it would be much nicer with plants than without. And I cannot say what these materials were because it's proprietary information of phosphoridec, but I just wanted to show that, you know, I work in many different places across the globe, so and I always tend to use locally available materials. So in parallel, before this demo site in the laboratory, we tested different kinds of organic materials locally available in Taiwan, and built 2 different pH reducers, mini scale, as you will see on the next slide. And we looked at the pH evolution over time. And here you can see that just, you know, okay, after 5 minutes in the first reducer, I didn't say we start with 13, pH 13. So after 5 minutes we had 10, after half an hour we had 7.5, 8.5, and then it decreased further with time. So because the demonstration site project had such poor hydraulics, I decided to build a mini experiment to show the concept to my colleagues in Taiwan and to demonstrate the concept. And what we have here is two reservoirs with real sewage brought from the farm. It was on the roof of the civil engineering building in Pintung. So in one line we have here a slug filter, constructed wetland, and pH reducer. Here we have constructed wetland, slug filter, and pH reducer. And we monitored pH in these systems for more than 180 days. And this was the influent concentration. We have number of pore volumes that were passed through the system, and so here we have, as you can see, of course we get decrease over time in pH for basic oxygen furnace slug in constructed wetland. In this constructed wetland I actually mixed slag and gravel, so it was not just gravel, so that's why it was high at the beginning. And but the major point I had to prove was that it is possible to keep pH throughout below rise. And project in Taiwan gave us a chance for a project in Brazil with ArcelorMittal, and we traveled there in January. Actually what happened, I attended a conference, Steel Slag Industry Conference in September, where representatives from Brazil were present, and this is ArcelorMittal site in Vitória, in a northern state in Brazil, and they use water from this lagoon number 6 for their steel production. But it is heavily polluted with algae because of all phosphorus that is coming from favelas, from urban areas, and all lagoons are connected in series there. So basically the way it looks like, ArcelorMittal built this 3-meter high wall, but and favelas, the urban areas are behind, and all sewage water is percolating under the wall, flowing into lagoon, which has a beautiful green color. So what we are hoping to do, and we will go there in June, I'm currently designing the system. Again, even though we proved that our systems are robust enough to work in northern climate and in subtropical climates, we always have to start with a smaller system before going for a bigger one. So we are going to build 2 systems across this road just to prevent, to treat this raw sewage water before coming to this lagoon. And Gunnar already spoke about this, and I don't know how I'm doing with the time, but I just wanted to mention that not only that we are passionate about phosphorus removal, but we always have to keep in mind that we have to find a way to actually recover this phosphorus. And I'm very impressed with Sweden and really honored to be here, because you are the only country in the world who actually has some requirement for phosphorus recovery before 2030. And I speak about Sweden everywhere I go. So, and thanks to Professor Edman, I'm part of the project to trigger phosphorus. So these are just some updated references for you. This is us in the press, and in this article I wanted to emphasize this article because I explain very well all the obstacles to progress, e.g. all the obstacles why we cannot actually make invention and do something about water quality. And summary of accomplishments, so considerable amount of work, 43 publications, lots of publications, working across 5 continents, various research proposals at the University of Vermont. Personally today I would say that my major really achievement in the last 2 years is that I managed to implement and validate phosphoridec technology in 3 major watersheds, given the difficulties with and obstacles from governmental regulations. Thank you for your attention.
Great, thanks, Alexandra. for this overview, really impressive. And I think you have taken on the word mission.
Yes.
I'm sure there are questions now. You were the first one.
Thank you for a really interesting talk.
Thank you.
I had a question quite early on, talking about the steel slag.
Yes.
Me too.
Talking about the steel slag, I had a question about this rejuvenation of the material. I don't know if I missed something there. Could you please explain a little bit more what you mean by that?
Yes, it's basically, am I allowed?
Yeah, you're online.
No, okay. It's basically what happens is if you have the filter, doesn't matter if it's in a column or rectangular, and you run it for a certain period of time, then you can close this filter, you can drain this filter. When you start feeding it again, it regains its phosphorus reduction capacity. Okay, so we we gave it the term phosphorus regeneration or phosphorus rejuvenation, because you can actually prolong phosphorus absorption by modifying the operating parameters of the system.
Yes, I noticed it myself in my previous work, but could you explain something about the mechanisms about it?
You know what? I'm pretty. I had slides on. There is a lot of mineralogical changes that are occurring. My personal belief is that that bacteria play the major role. But I had no chance at the time when I was doing this experiment. I was a postdoc in Montreal, and I had no chance really to go into mechanism. That remained like my big, if I do get a chance, I would like to go and investigate, in reality, the mechanisms. So I observed this at synthetic solution first, and then I repeated the experiment with real agricultural effluent. I made comparisons between different steel slag types, because for me personally it was very interesting, because I work with so many steel slag materials, over 15 different steel slag materials. Why it's happening in one and not in the other?
Yes, and if I still can ask, so did you test whether the phosphorus content still was the same, although it regained the capacity to trap more phosphorus?
Yes,
or did you lose some of the trapped phosphorus in the process where you rejuvenated?
No, I did not lose any phosphorus. It was trapped, but the important point is that even though we get that peak when we start feeding again, and the same happened with E. coli, what is happening is after resting, your pH goes up. And then so you have your pH goes up, and then your phosphorus and your E. coli reduction goes up from 0 to 100, but it goes down very fast. Also, not as in the first period. So, there needs to be more work done.
Extremely interesting.
Thank you.
I have a question.